Hello and welcome to my presentation where I'll be talking about my project where I explored music generation with AI. As a presentation overview, first I'll be explaining what neural networks are and how they work. And then I'll be going through some of the initial approaches that I tried with music generation. Then after that, I'll go through a model that I found online from a research paper called Deepbach. And finally, I'll talk about future plans. So, as far as applications go, neural networks have a wide range of them, but I believe that they excel mostly in natural language processing and computer vision. So, language processing uh, is a computer making sense of human language. So, a task in natural language processing might be autocomplete. And then computer vision is making sense out of images. So, a task for that might be recognizing people versus cars as seen in this picture. So, next I'm going to talk about what neural networks are or how they work. So, I think of neural networks as a massive calculus optimization problem. So you have this model with inputs and outputs, where the inputs are your x values and then the outputs are your target y values. And so your model takes the inputs and applies a big function to it and predicts the output. And so the resulting error between the y actual and the y predicted is then used to optimize the parameters or the weights and biases. And so when you're training a neural network, at first the error is going to be really big, but as your network goes through data and the parameters update, then the error will reduce. So recently, there has been a boom in natural language processing, and this has actually led to the advancement of music AI because music AI and natural language processing are actually very similar. So, as an example, think of autocomplete, where the task is to use previous words to predict future words. Then a similar task in music AI would be using past notes to predict future notes. So there's definitely a lot of similarities between the two fields. And one type of neural network that they both use are recurrent neural networks. And these are neural networks that deal with temporal data. So where context within the sequence matters. So I had two initial approaches and they had a similar process to them. And the X data was sequences of a certain length of encoded events. And then the Y value or the target would be the next event. And this would be one hot encoded. And so the model ultimately would be predicting a probability distribution for all the distinct events. So, and then that to generate the music, the um, that distribution would be sampled from. For the first network, which I called on off, it encoded the data or the pieces using note on, note offs, and rest. So note on would just be turning on a note or pressing down a note, and then note offs would be releasing it, and the rest are just waiting a certain amount of time. And so this is just the tokenized view of the data, but ultimately it would be integer encoded. And here is what the network actually looks like. So first you have the input of sequences of events, And those go through a layer called an embedding. And what this embedding does is it projects the integers to a vector space where through backpropagation, similar events will be projected to similar or closer vectors geometrically. So notes in a C chord will be much more similar than the lowest note of a piano and the highest note of a piano. And the at the output of the embedding would then go into an LSTM, which is one of those. That's a type of recurrent neural network that deals with the temporal data, and this then goes into a fully connected, just regular dense layer of, and that would output the note probabilities or the event probability predictions. And so I'll go ahead and show that what that music produced. And it's not great, as you'll see. So obviously not the best music, and reason most likely is because of the note on, note off trend. So um, the network has to remember to turn off notes after turning them on. And I think that was giving it trouble as it wasn't turning off notes. And so this next network aimed to fix that. And to do that, I dealt with time as durational. So an event consisted of two parts, the signal and the duration. So it could be either be a note on or a rest, and then there'd be duration for each. And so here is the what the network looks like. So you have your input of signals and then your durations, and they both go through an embedding layer. Then that goes into an LSTM, and after that, the signal probability predictions are made. And using those predictions, the durations are made because the durations rely on the the uh, the note that is being predicted or the rest. That's pretty influential. And so here is that network, one of those pieces. So this network produced some really interesting music, and it's definitely a whole lot better than the on-off network. And this really showed to me that data engineering is a very important part to music AI and really machine learning in general, because the same amount of data was encoded, but just in a slightly different way that allowed the trends to be extracted more easily. That being said, there's still much to improve on as the music is kind of all over the place and there's no rhyme or reason to it. And so I ran out of ideas at this point, and I didn't really have too much inspiration, so I decided to look into someone else's implementation. And what I settled on is a model called DeepBach, and this used Bach chorals as data. And what was interesting was the data was highly structured, and each choral was separated into four voices. And also, another difference was the sampling method, which was Gibbs sampling. This was used to generate new samples. And so, Gibbs sampling is used when you want a sampler from a joint distribution, but you cannot directly do so. And so, to do this, you sequentially resample from conditional distributions. And so, in terms of DeepBach, the joint distributions would be every single the probability or the distribution of all the notes in the voices and relative to voices and time steps. And so to give sample it, you start out with a piece that is initialized randomly, and then it would you would continuously resample notes. So you choose a note at random from a random voice and time step, and that would be resampled given the context around it. And so this would be repeated for a certain amount of times and would give you a new piece. And so for deep walk, these samples for the X aspect of them would be the past, current, and future notes for each part, as well as some metadata, which include key signature, subdivisions of the time, and the fermatas, which are signal for ending of phrases in music. And then the Y would be the current note that is being resampled. And an important part of this of Deep Bach was each voice was modeled separately. So when I say that, I mean if you want to resample a voice from the soprano voice, then you'd go to the soprano neural network, which would use all the other voices, but uh, they're just separate for each voice. And so here is what that network looks like. And so you have the past, current, future sections, and then for each one of those, you have all the different voices and the metadata. And so those go through embeddings and LSTMs and just a regular fully connected layer, and then they combine and predict a note for the one that is being resampled. And so here is that. So I was really impressed with the music that this generated, and it was amazing that came from this randomly initialized state and just many iterations of resampling, and it's just convincingly Bach-like. So really, I think the strengths of this model come from two different aspects. One is the Gibbs sampling, and two is the highly structured data. So the Gibbs sampling was a clever way to generate music, and it showed me that sampling is actually a really important part of music AI and makes a lot of a difference. And as far as the data went, it was once again encoding the same amount of information, but just in a different way. And the results are a whole lot different. And the different voices allowed the network to extract relationships a lot easier. So I have one semester left, and I definitely plan to look at a few other models and possibly tweak my existing models, more specifically the durational one, because I think that produced some pretty interesting music. And so I want to give credit to Dr. Wanchunzi Yu, who's my mentor, and also the creators of Deepak. And so thank you for watching. And here's some sources. Here's the Deepak paper and a book that I use called Deep Learning with Python. Thank you.